Welcome to the second video in our Class 18 series of lecture videos. I thought I would begin this lecture video with a cartoon description of a Grignard reaction and try to explain what's going on in it. A Grignard reaction is also known as the dissolving metal reaction because we typically have large chunks of metal, either lithium or magnesium, that float around in our ether solvent that we use. Of course, those metals don't just dissolve in polar aprotic solvents. However, they do appear to dissolve when we add a halogenated hydrocarbon to those solvents. And so what's going on, of course, is we're forming alkyl lithium or Grignard reagents, and we can think of that dissolving process as follows. So let's take the example of methyl bromide. Here we have a chunk of magnesium metal. You might have a magnesium atom that's sitting at the surface. I've drawn it with a hexagonal kind of shape. You're just going to have to pretend that that is a single magnesium atom. And metals are pretty strong reducing agents, so it has the ability or potential to push an electron into our methyl bromide. Now, this is unusual, right? When our methyl bromide molecule bumps up against this chunk of magnesium, an atom at the surface just pushes an electron onto it. And we get something that we call a radical anion. So, and I've drawn it in this strange bond line, Lewis structure where we've got, our methyl group bonded to the bromine. And I put that electron that we took out of the magnesium atom on top of that carbon-bromine bond. What does that represent? Well, really that electron is in the lowest unoccupied molecular orbital for methyl bromide, and that would be the sigma star antibonding molecular orbital of the carbon-bromine bond, right? So that's where that electron is. It's kind of difficult to represent that or depict that with a Lewis structure, but that is usually what we do. We generate these weird radical anions. My magnesium atom now popped off the surface. It's a cation. It's solvated, presumably by ether molecules. This radical anion is not stable. Of course, putting an electron in that antibonding carbon-bromine molecular orbital weakens the carbon-bromine bond, and in fact, it breaks apart into a bromide anion, a methyl radical, and of course, we've got our magnesium 1+ cation counterbalancing that negative charge. Magnesium has an additional reducing potential. It likes to get rid of 2 electrons to reach a closed shell. So we'll go ahead and transfer 1 more electron into our singly occupied p-like orbital of our methyl radical to give us our, in this case, our methyl carbanion. And now we have our magnesium 2+ cation floating around solution and a bromide anion. And this process repeats again and again. Your little magnesium atom sitting at the surface, keep pushing electrons into our halogenated hydrocarbons. If we've done our stoichiometry correctly, our chunks of magnesium dissolve. So that, in a nutshell, is a Grignard reaction. Hopefully I can find a video on YouTube of these dissolving metal reactions and show it during the actual class time. So let's consider Grignard reacting with water and alcohol. I think in the first video I said that they are very basic. We cannot form them in the presence of a polar protic solvent, so we have to make sure our ether is anhydrous, does not contain water. And again, if there were an alcohol present, the Grignard would simply react with it. How would it react? Well, the carbon is really the atom that owns the electrons if we represent our Grignard with this polar covalent bond. We've also represented it in an ionic sense where we can see quite clearly that it is carbon that owns those electrons. In a product solvent, whether it's water or an alcohol, the hydrogens are electropositive. Oxygen is much more electronegative, so of course we're going to take our carbon and use its electrons to form a bond with the hydrogen, and of course we'll give the electrons in this hydrogen-oxygen bond back to oxygen. We can think of this as an acid-base reaction. In this case, water is our acid. Water is not very acidic. We say its pK is about 15.7, but hydrocarbons are even less acidic. Their pK is around 50. And so if you were to calculate a KEQ for this, it would be 10 to the 50 minus 15.7, which is much, much greater than 1. We push all the way over to the right side. We liberate propane gas. As long as we're doing this slowly, it doesn't catch on fire. And then we have magnesium salts. So in this case, magnesium chloride hydroxide salt as an inorganic byproduct. Similarly, you could think of this propyl magnesium chloride reacting with methanol to generate propane and chlorine magnesium methoxide salt. Grignards are strongly polarized. Like I said, it's really the carbon that's electronegative or delta negative. It owns those electrons. And they react with aldehydes and ketones, carbonyl groups, like I said, to form carbon-carbon bonds. Let's take a look at propyl magnesium bromide. Really doesn't matter what our halide is. And benzaldehyde, for example. We're going to form a carbon-carbon bond using those electrons. And it's kind of like a little bit of a optical illusion, right? We have 3 carbons in our propyl magnesium bromide. We better make sure the tail that we appended is 3 carbons. 1, 2, 3, and there's our bond. Now what happened to the double bond? It broke. We pushed a pair of electrons up onto the oxygen. It's got a formal negative charge. Our magnesium 2+ is still hanging out, as is our bromide. Then we do a subsequent aqueous acidic workup. Here we have, it's usually HCl. Sometimes we just say H+, right? H3O+, H2O. And here we've got the alcohol that we formed. I'm not explicitly drawing the hydrogen that's on, the carbon that's bonded to the hydroxyl group, because I know that it's still there. We would expect a racemic product that Grignard could add from either the top face or the back face. And of course, we've got our magnesium chloride bromide inorganic salts as a byproduct. So last page of notes, and we'll call it quits on this video. Dry ice. Solid carbon dioxide is a great way to quench Grignards, that is to destroy their reactivity, without catching yourself or other people on fire. So let's say we took benzyl bromide, we added some magnesium, we made benzyl magnesium bromide Grignard, but we made too much of it. We couldn't react it with whatever it is we wanted to use it for. Instead of adding water cautiously and hoping not to catch on fire or blow up, we could just take our solution of Grignard and add it to finely ground dry ice, because dry ice is very cold, minus 78 degrees C, and it's full of these carbonyl functional groups. Our Grignard will just attack that carbon, the heat will be absorbed, and nobody will catch on fire. That's a good thing, right? And so what we do is we've extended our benzyl bromide by a carboxylate anion, and of course we're using this carbon dioxide in great excess, and our carboxylate anion is counterbalanced by magnesium 2+ and a bromide anion. But of course, if we were to add like a strong acid like HCl, we would lose magnesium, chlorine, bromine salts, and we would generate a carboxylic acid. So it's nice to know that we need not only limit ourselves to sp3 type carbons for our Grignard reagents, we can also form sp2 type Grignards. We could mix in phenylbromide or bromobenzene with magnesium and generate phenyl magnesium bromide, or we could mix in vinyl bromide with magnesium and generate vinyl magnesium bromide. We could even generate Grignards with sp hybridized carbons, but that'll be subject for a future class lecture. That does it for this video. I'll see you in the next.